signal that is recorded, it may be something like this, which makes sense here because the particle is moving with some velocity away from the transducer, far from the transducer. And what is delta t in this kind of scheme? What would be delta t? Delta t in this scheme, what exactly is? Or you? Yeah, but in this kind of plot, no? In this, when I'm talking about the first pulse and second pulse, what could be delta t? Or what would be TPRF? Oh, what's the difference between delta t and TPRF? How are you? El primero es la diferencia entre pulsos. La diferencia como que en el tiempo de llegada de este pulso, digamos T1 y este tiempo de llegada T2, entonces delta T sería T2 menos T1, ¿no? Correcto. Y la otra, y este TPR, ¿qué sería? What could be TPRF? Is the time that passed between applying the first pulse and applying the second pulse. So it's, the operator will determine when they apply the pulse. Apply pulse and wait a time, no? TPRF, to apply the second pulse. So the second pulse, the waveform has changed. So there is this relation, right, between these arrival times, T2C1, and TPRF, that is the time that we wait. And that relation is approximately the relation between the velocity of moving, the particle moving, for example, and the speed of sound of the acoustic wave. Okay. But the problem is when we don't have only one particle moving, like this example, and we can find very fast, this delta t, just looking at the signal, maybe calculating the maximum, for example, time or the minimum. In a more realistic signal, the first pulse will generate this kind of echo, and the second pulse will generate this kind of echo. So it's difficult to say what is the delta time, right? So we cannot say that in a more complicated signal, because there is not only one arrival time like this. So what we can do? That's what is two possible solutions are using the slow time, and then other is using a moving window algorithm. In the slow time, we just fix our attention in one position, or one center position and one window, and see how this window is changing, how the amplitude is changing, or how the waves are changing in that specific position. And in the moving window, we will do that. For example, fix a window in the first pulse, and the second pulse we just test the correlation between, for example, this window, and then this window, and then maybe this window, for example, and we test all the correlation between one fixed position here and all possible moving positions in the other pulse. So, applying correlation, we will find one position that correlates more to this position. In this case, this looks like here. So that way we can calculate delta time or shifting time based on calculation of correlations. Yep. Okay. I think we mentioned the slow time approach first. I think I also talked a little bit about this in the video from last week. But basically, it's saying that the received signal in an instant I will be the received signal in an instant 0 shifted in time. So that's minus I Ts refer to the shifting. In fact, Ts here is how much? This Ts would be equivalent to our delta time. It's like, for example, if in this moment the waveform look like this, and now the waveform look like this is the same signal, only shifted some delta time, right? So shifting here is this minus delta time. If we would do a third pulse, probably the signal will look even farther, right? Something like this. And we will have arrival time T3. So for example, what is the difference between third pulse and first pulse? Is T3 minus T1, and that you can see that it's double delta T, right? Double of this individual, the first different delta time between second and first. If we want 4, we will have 3 delta time. So this I delta time refer to ITS refer to how much it's shifting, depending on the pulse number of pulses. Okay, so this TS refer to delta time. And the relation is the one that we just saw in the previous slide, right? But remember that this signal is not as simple as this. It's something more random, with more scatterers. Okay. And then we try to write this signal as a complex exponential. So amplitude, complex exponential. Some attenuation, some shifting. I think this 0 corresponds to something like this. If we have a pulse, and we send a pulse, the red blood cells are in some area, moving in some area with some speed. This 0 here refer to basically this distance, the distance until the vessel. So the signal of interest for us is like nothing, and only the interest is around the vessel. Here we will have some signals that we will look if they are shifting or not. Okay. In fact, before that, there can be also scatterers from the tissue, right? But maybe we have some signal too here. But it's possible to eliminate them with something that is called wall filters. I think few slides I will mention this too. But at the end, we can just delete this part and keep only the moving parts, the signal that come from the movement of red blood cells. That's why in that signal that corresponds to only movement, before the movement is almost 0. So it's like the signal of interest again is shifted, basically a distance related to the depth of the vessel. The frequency of the signal that is received by Doppler is not the F0, the original F0 that was transmitted. It will be changed. And how much is changed? How much is changed is given by this factor, this factor alpha. In acoustic attenuation, in acoustics also the alpha is a common variable used for the attenuation. I think we didn't mention this property, but this alpha here is not related to this attenuation. Okay, it's just a factor, and if you see this factor will be 1 when the velocity of the particle is 0. If the velocity of the particle is 0, it's not moving, there is no moving object, then it's 0 and this alpha is 1. So basically the variable that multiplies time is the original F0. It's like the frequency won't change when the particles are not moving. But if the particles are moving, the frequency that is F0 times alpha, right? Like a 2 pi j to pi 0 f at time. This is the main part. Means the frequency is this. So basically, it's F0 multiplied by some factor that depends on the velocity of the particle moving. Okay. Yeah. Any question with this? I think this is the moment, right, to ask questions. Something about this equation is not clear? And what is this? This is this term, right? It's ITS, or I delta time. Basically, I, the number of pulls, delta time is 2B over C, CPR. It's clear? This equation? Okay, at least I hope you can see, right? The important part here is this. I think we are that refer to different pulses. This alpha time today is how much the frequency is changing due to the movement. Okay, so it's like we have this signal. We have this signal, and we can do operations with this signal. So this is like a representation of the signal of interest that come from the red blood cells moving. So one first thing that can be done is the modulate. You remember what's the modulation? Or what's modulation? For example, if I have some signal, let's go GT. GT it can represent some signal and may have some Fourier transform. I will call just this, the representation of the magnitude of the Fourier transform as a function of f, for example. Right? This is one signal and its Fourier transform. Assuming that this is a real signal, the Fourier transform amplitude, magnitude will be symmetric. What is the Fourier transform if I multiply this by this product? What is the Fourier transform of this expression? What is the difference between this and this? Basically, it's multiplying some signal by complex exponential. So that signal multiplied by complex exponential could be, for example, let's say, I say that the pulse is, or the GT, maybe is this signal, for example. The complex exponential will be some oscillation that has real and imaginary part, but the real part will look like sine. And what would be the product? The product of GT multiplied by complex exponential. If you look at this, it will look something like this. So basically, the original signal will become like an envelope of oscillating function. So that, and we can call this like a modulated oscillation, but not oscillation like with fixed amplitude, but oscillation with some GT amplitude, depending on one thing. Okay, so when I talk about the modulation, it's the process of going from this red modulated signal to the blue signal. What we can do to obtain from the red oscillating function the blue signal. What can we do to this red signal? And what we can do is, if we have this signal, and we want to obtain this signal, what we can do? To this signal, we can multiply by another complex exponential with different signs here. If we multiply that, we obtain this. And multiplications by these factors, complex exponential, positive, negative, electronically is relatively simple. Okay, so this modulation or the modulation process are simple tasks for electronics. Here is possible to do, and we can obtain back this demodulated signal. So here, when we said the signal can be demodulated, it's just multiplying all this by E minus K2IF0. That's why this minus entered here. It's minus 1. So only change that from this to this. Since the time t is referred to the moment of transmission at a fixed depth or fixed time, the expression can be written as this. So I will write that expression, the demodulated. Okay, so after the modulation, we have the signal. Yes? One question. Yes. ¿De esto? ¿Esto? Ah, ya. No, esta parte está aquí. Esta parte es esta. Este 2 de 0 es justo lo que explicaba que, digamos, de forma general es una función de tiempo. Pero para el Doppler, digamos, es una función que tiene una parte exponencial compleja, oscilatoria, que está shifteada también, ¿no? Está shifteada esta cantidad. Y esta cantidad está shifteada porque la señal de interés no empieza, digamos, desde aquí. Empieza desde la vascularidad, que está a una profundidad de 0. Entonces, como que, si empezara en 0, sería como que, bueno, algo así. Pero si empieza en la vascularidad, la señal de interés va a ser algo que más o menos está a la profundidad de 0. Este 2 de 0 es porque es ida y vuelta, ¿no? El tiempo que demora es ida y vuelta de 0 más de 0, 2 de 0, entre velocidad del sonido, ¿no? Simplemente se refiere a este shifting, porque el BC no está a la profundidad 0. Pero esta parte sigue acá, esta parte está acá. También esta parte importante. Okay. Y the slow time No, this signal still is in the fast time. No? It's in the time that depends on the t, that is the time of the waveform, no? This kind of axis. But now we will fix time and try to see how the signal changed with different pulses. So this is a representation of the slow time signal, but more mathematically. More mathematically is basically this equation for a fixed time. So if we fix the time for some, we're going to do this for all possible times. But let's say we fix this for time to 0, for example, or t1. For that time t1, this term and this term are represented by this phi c. Phi c could be alpha minus 1, sometime t sub 0, or t sub 1, minus 2d0 over c. This is replacing a variable. But the variable of interest here now is I. So we will now focus on how different pulses are changing the signal in one specific time. So this is what we saw before with the slow time signal. I think in this part, we said, okay, we fix our observation point in one time and see how the signal is changing. And the signal is changing oscillatory, or with some oscillation. So basically, this oscillation, more mathematically, could be written as this. Some oscillation that will depend on the number of pulse, and on the pulse, and with some shifting here in the phase. Okay, which makes sense, because we saw that this the slow time signal were oscillations, so we still have the oscillation here, the oscillation form with complex exponential.
Esa parte, shifting de letras, dígase, está en base al B también, ¿no? Al BC. ¿Por qué no está?
En vez del B sub C, ¿te refieres a esta parte o a esta parte?
A la otra, la de la derecha.
A esta.
Sí.
Esta es, no depende de I, no depende del número de pulso.
Sigue dependiendo entonces de la distancia. Porque
Sí depende de la distancia de observación, porque aquí depende, aquí digo, una distancia de observación asociada a T1, y T1 está asociada a una distancia de 1, igual a 2, C por T1 entre 2. La relación. Cuando digo T1, aquí me refiero a una distancia de observación, que es igual a esto. Y en este punto, bueno, esto no depende del número de pulso, Hay una fase, un término de fase que no depende del I. Okay, and then one change variable used to have a dependence in the slow time with a variable of time instead of a variable of like a number, 1, 2, 3, a sequence. So you just notice that we use the variable time equal to I TPRF. So we use the place, instead of thinking about number of pulse, we talk about time tau. Time tau. So everything the same except here. This I TPRF changed by tau. So the signal in the slow time has this form. And don't forget, our interest, the thing that we can calculate is this v, the velocity of the particle. how can we find this V? No? Assuming that we know this signal, no? We will observe this signal, we will have some representation, no? In the slow time that oscillates. How can we calculate from this signal oscillating in the slow time V? No? And to do that, we use what is called the derivative of the phase. What is the phase in a complex exponential? For example, a complex number, right? 3ai, for example. Or j power. In this complex number, what is the amplitude? The amplitude is 3, right? And what is the phase? Is pi over 2. It's basically the amplitude of some x e power j angle of x. A representation of a complex number in amplitude multiplied by complex exponential, and that argument, the exponent in the complex exponential is what is called angle or phase. So what would be the phase for the slow time signal? The phase angle of is tau. What would be? What is the phase? What do you think? From this expression. From this expression, what would be the phase? Minus, yeah, correct, fine. F0. Correct, this will be the phase. So from this signal, it's possible to calculate phase. In fact, that's what the Fourier transform can do, right? When you calculate FFT of that some signal, give you the amplitude, you can calculate magnitude or ups from that, and also angle from that Fourier expression in the complex domain. So it's the same. Okay, so if this is the phase is something again that can be calculated. Okay? We can see the signal demodulated, and from that demodulation, we can get the slow time signal very easily. And from that slow time signal, we can just calculate the phase. So this task also is something doable. Okay, so assume we know this. What can we do to calculate V? What can we do to calculate V? We can derive. This also with the notation phi. So we will derive phi with respect to tau. We are looking at the slow time signal, and we derive with respect to the variable of the slow time signal. And how much that would be? In tau, this is constant, right? So the derivative of that is just 0. So only focus on this part. Right? It would be minus 2 pi f0 multiplied by 2v over c. Okay? Or what would be the same, right? The velocity would be the derivative multiplied by minus c over 2 pi f0. Okay, yeah, and that would be how we calculate the velocity. It's taking the derivative with respect to tau and multiply that by minus c over 2 pi f0. I think you are familiar with this phase terms. No? Remember when FFT? Remember how was the phase? No, for example, when you have AJ omega t, right? Omega 0 t. What was the phase? Remember, it was omega 0 t, right? So you graph that versus time, it's something like this, or something like this. This represents omega 0 time. So, yeah, the phase is something that is linear. Typically, no? We want this to be linear. It's not always linear, but in one complex exponential is linear. How much is the derivative of that, for example? The derivative of the phase with respect to time. How much is in this case? It would be only omega 0, right? Yeah, the slope, no? La pendiente. So some constant. Right? So the phase is something that, yeah, can be linear, and deriving that will be constant. So this is, in a sense, no, in some ideal case, no, when we have complex exponential, this will be constant. Okay, and that constant multiplied by minus c over these 2 pi f0 that are also constants will be some constant value, and that is the velocity that can be calculated at every time, no? At every possible time. We can do that process for t1, t2, no? All the points, all the times across the fast time. And it's just a repetitive process. If this derivative can be calculated for each value of time, an axial profile of the velocity can be reconstructed. We can calculate this v, the velocity for time 1, v for this time, no? Talking about a more random signal. We can calculate the velocity for every possible time. Okay. And I think we also see a little bit of this phase. In Doppler, no, the phase is very important. No? How can we calculate the phase? Can we calculate the phase, for example, from when I did this, but it was the complex exponential expression of the slow time signal. He's looking at the exponent of that, and that is the phase. Or another way to calculate the phase phi is using what is called the in phase x and the quadrature y, the I and Q signals from a scatter. It's like the complex exponential signal that I was mentioning before, that depend on the slow time. I mentioned tau here, for example. This signal, it was a complex exponential, remember? It was a complex exponential. And this signal has, obviously, two parts. A real part and a complex part. Okay? So the slow time signal basically have real part and imaginary part. And if we put some j multiplied by the imaginary part, we have the signal back. This is this exactly. And what he's saying, this is like that. How much is the phase, right? The angle. If we have this expression in real plus imaginary, what is the magnitude of this? The magnitude is, remember, x tau squared plus j tau squared, e complex exponential, and some angle, right? Some angle. At an angle would be the tangent inverse of the imaginary divided by the real. Our slow time signal also can be expressed in this form. When we have the real and imaginary part, the in phase and quadrature terms of the slow time signal. And here, no, the phase is what is next to this complex exponential, the j of the complex exponential. The phase is this. That's why here mentioned the phase is the tangent inverse, no, of y over x. Imaginary part and real part. And what this is mentioned because equipments on ultrasound can get you these signals directly. The equipment will give you the x signal and y signals. No, the equipment can give you those signals. In fact, they give you the signal for this time. No? This has some fast time. They give you the x and y for the fast time, but just taking, just fixing again one time and looking how it changed with different pulses will give you x tau and j tau. Okay, so we have this phase is tangent inverse of y over x. But for our interest is the velocity, we say that is phase derivative, the derivative of the phase with respect to tau. So we need to do that. Derivate phi with respect to tau, and is the derivative with respect to tau of tangent inverse. And that is the derivative of tau, the tangent inverse of y over x is the expression the derivative with respect to tau of phi is equal to x tau multiplied by, what is this? Y dot tau is the derivative of y with respect to tau. And here I will write it in this way, okay? More common for us. Minus y tau multiplied by the derivative of x with respect to tau divided by x tau squared plus y tau squared. Do you remember that the derivative of the tangent inverse had this form? Maybe you saw that in calculus, right? In some calculus 1 or 2, maybe? Well, you can use it in this expression for the first time, maybe, the derivative of tangent inverse. Needed for the derivative of the phase. And that expression, just replacing x and y here, will give you this, and this is related to the velocity, right? It's minus 2 pi f0 2v over c. So this will look like a signal. And that, oh no, this will look like a, some signal right? Yeah, it will look like a signal, and you make this equal to minus 2 pi f0 to v over c. And that should be, we expect it to be constant. This should be a number for all the values of tau. It's like here, right? What is the derivative, for example, of this signal? Is omega 0, right? But if it was not like this, if it was, for example, something like this, some oscillation or some noise, maybe the derivative of that will look like something like this. More or less, no? For all the values of time will be omega 0, but with some noise. So in real signals, this may look not exactly one single value, but some value changing a little bit. with some noise. But then you can take, okay, the average value of that. And when you find one single value, okay, you say, okay, this single value is related to V, the velocity of particles in that depth, with this expression. In practice, we do not have access to the slow speed continuously, but samples to a TPRF sampling period. For this reason, it's required to use finite differences. This is basically just mentioning that xt and yt are not like a constant or continuous signal. It is only valid when this is TPRF, when it's 2 TPRF, 3 TPRF, and so on, and so on. It's like a discrete signal, but the derivative of discrete, the derivative of yt with respect to t. Remember how is the approximation of this is like, for example, t minus TPRF, for example, TRF divided by TPRF. This is one sample minus the previous sample divided by the difference between these two. And that's basically what is written here. We change the derivatives y by this form. Y divided y at some time I is associated with time I, associated then with I minus 1, one previous sample. And divided by TPRF. So if we replace here, we have 1 TPRF here. Here also 1 TPRF. And that 1 TPRF that is here multiplying is just mentioning here like this. Put it outside, and you have this signal. The derivative y, derivative on x, and the other are still x and y, x squared, y squared. The good thing here you want is like we have a term xi, yi here, and we have term yi multiplied by xi. Can be cancelled each other. This can be cancelled. So we have only this minus yi multiplied by this minus xi minus 1. That is here. Minus xi, yi minus 1. Xi, yi minus 1. Divided by the same denominator. Therefore, the velocity can be estimated as, just reorder it, this here, and this here. And this expression is the one that I mentioned, minus 2 pi f0 TPRF should be over 3. No, it's okay. This TPRF is because this one goes to multiply. Okay, so basically we have here the discretized slow time signals x and y, the components x and y of the slow time signal, and we usually do this calculation. And that value should be the same every time. Should be the same every time. From going from pulse 1 to pulse 2 should be the same as going from pulse 2 to pulse 3, and should be the same going from pulse 3 to pulse 4. In practice, it won't be always exactly the same. It will have some noise, but we can just do an average of all these values for all the different pulses. Okay, let's continue in one moment after the quiz. ¿Listo? Ahora saquen una hoja, por favor. 25 en profundidad. Es decir, el elemento 52 será el último que dispare la onda de ultrasonido. Ok, pero ¿cuál es la distancia entre elementos? La distancia entre elementos es 0.5 milímetros. Podría decir el D. 0.5 milímetros. Entonces, un centímetro. ¿Cuántos? Entre el elemento 32, 33, ¿no? ¿Cuántos deberían haber para hacer un centímetro? Aquí, ¿cuánto hay? Un milímetro. En dos elementos hay un milímetro, tendría que haber como que 20 espacios. 20 espacios. ¿Y aquí sería cuánto? 51. El elemento es 51, ¿cierto?
No es 61.
Porque tendría que haber 20 espacios para que lateralmente haya un centímetro, para que todo esto sea un centímetro. Ya, entonces, el elemento 50. ¿Y eso por qué? ¿No? Porque cuando está enfocado, habíamos dicho, ¿no? Que los elementos van a disparar a diferentes momentos, ¿no? ¿Quién dispara primero para llegar aquí al mismo tiempo? Los que están más lejanos, ¿no? Disparan. ¿Y quién dispara al final? El más cercano, ¿no? Justo el que va a estar, digamos, encima, ¿no? De esta posición 1,5 centímetros. Entonces, sí, sería encontrar ese elemento y, si no me equivoco, ¿no? Un centímetro de 0.5 da 20 espacios y tendría que ser, entonces, el elemento 51 sería falso. ¿Sería falso eso? La siguiente es, ¿no? If no steering is used. Ahí se puede calcular, ¿no? O sea, básicamente calcular qué frecuencia va a ser en este caso. 50% menos, 2.5 MHz. ¿Cuál es la longitud asociada a esta frecuencia? Si no me equivoco, sale 0,6 milímetros. ¿No? O sea, entre eso. Y habría que ver, ¿no? Si esta relación se cumple, ¿no? Cuando no hay steering, habíamos visto que el criterio es esto, ¿no? Es D entre lambda, ¿no? Que sea menor o igual a n menos 1 entre n, donde n es 61, ¿no? 60 entre 61. Porque es aproximadamente 1. Entonces D, pues, tendría que ser menor o igual que lambda, ¿no? Aproximadamente. ¿Y D cuánto es? D es 0.5 milímetros. Eso es menor o igual que 0.6. Sí, ¿no? Entonces sí es menor. Entonces, ¿verdad? Sí, se cumple. Y la tercera, ¿no? Es que el arreglo está enfocado, ¿no? En 0,5 centímetros. Entonces, no, si ese es el elemento 31 en el centro, 0,5 estará por acá. Entonces, claramente, ¿no? Este elemento que está arriba es el que dispara al final, enfocado en esta posición. Más bien, ¿quiénes disparan primero? Los elementos 1 y el elemento 61. Y disparan, pues, porque tienen más distancia, ¿no? La idea es que todos lleguen juntos a esto. Entonces, los que están más lejos disparan primero, ¿no? En el instante inicial, entonces ellos no tienen ningún tipo de retraso o delay. Quien debe tener más delay es el que está arriba, justo, el 31, el 31, arriba de esta posición. Ahora, ¿qué tanto, no? ¿Qué tanto retraso tiene este comparado con estos dos, ¿no? En la simetría? Y es posible calcular las distancias, ¿no? Tenemos esta Z0, ¿no? Y esta Z1, por ejemplo. ¿Cuánto antes tiene que disparar este elemento, o como he dicho, cuánto después, ¿no? Qué tanto retraso tiene que tener este, ¿no? Con respecto a este elemento. Dependerá de la distancia. O sea, es simplemente calcular, a ver, ¿cuánto es esta distancia? 30 por 0.5 milímetros, ¿no? O sea, 15 milímetros. Correcto. Y esta profundidad máxima es 50 milímetros. Entonces, por el teorema de Pitágoras, ¿cuánto sería esta distancia? Si no me equivoco, era 52 y algo. O más. 52.2 aproximadamente, ¿no? Milímetros. Entonces, digamos, ¿qué distancia más tiene que recorrer este con respecto a este, ¿no? La resta. O sea, básicamente la resta de estas dos distancias determina, ¿no? Qué tan antes tiene que salir, ¿no? O cuánto tiene que retrasarse este más bien, ¿no? Como que este tiene que, imaginariamente, ¿no? Si hubiera aquí 52.2 milímetros, empezar por aquí. Básicamente, bueno, 52.2 menos 50. Es este tramo. Pero la diferencia de distancia es lo que aquí importa, ¿no? Que es 2.2 milímetros, más o menos. 2.2 milímetros. ¿Y cuánto tiempo requiere, ¿no? Ese delay, ¿no? ¿Cuánto tiempo requiere de delay 2.2 milímetros? Dada que la velocidad es 1500 metros por segundo. Lo cual es lo mismo que 1.5 milímetros por microsegundo. Sería esto entre esto, ¿no? La distancia entre la velocidad. ¿No? Y eso sale aproximadamente 1.5, creo, aprox, 1.5 microsegundos. Entonces, imagine that the left leg, alright, will be larger than 3 microsegundos. Ese sería.
Literalmente yo llorando y diciendo, esta cosa no se entiende, ¿verdad? Sí se entiende. Pero necesitaba para llegar a esto. O sea, no se me ocurrió la primera vez. Yo estaba sacando lo del bicho y todo esto. Y saqué la Ah, ¿te vas a sacar todo? Sí. Ay, qué cólera. ¿Lo dejaste grabar?
No está grabando ahorita.
Sigue grabando.
Okay, continuamos. Let's continue with this Doppler thing. There are other formulations for the phase derivative that differ subtly a little bit and result in variance of the estimation algorithm. Following the previous derivation, one can use finite differences to directly approximate the derivative of the phase. It's basically saying that let's see. If we look at this expression, can we write this in a finite difference form, like we write yi with this? written like the phase at one instant minus the phase at the previous instant. You see? Would be like the phase at tau, instant tau, and instant tau minus TPRF divided by TPRF. I think this is the correct form to write this. Mhm. Right. Yeah or no? Let's see. Okay, let's use directly. No, this previous expression is the rest of two phases. Phase at one instant, and phase at previous instant. And here, there was some. Yes, the ratio between the slow time signal at one instant divided by the slow time signal at previous instant. No, you can write it as a magnitude. No, division of magnitudes and subtraction of phases. SI is the absolute value, magnitude, AJ 5. And the same, but in previous instant, or previous pulse, is the magnitude in the previous pulse, J, the phase in the previous pulse. Yeah. Yes, that could be. And just see why it shouldn't be like a phase. Phase of. Okay. Basically it's expressing the slow time signal at one pulse, slow time signal at previous pulse. You get this. No? If you divide them, you get this expression. Basically, the difference of the phases that is related to the phase derivative is this angle, the phase of the ratio, the division of two slow time signals. Okay, and then you can write the division of these two time signals as the division of the real plus imaginary part of 1, and real plus imaginary part in the previous pulse, I minus 1. No? How can we use operate here? This is multiplied by the this expression, but with negative sign. What was the name of that? Conjugate, right? The conjugate of the denominator. We multiply by the conjugate of the denominator with the same in the numerator. And in the denominator, then we have this j becomes j squared, this minus 1, with this minus becomes plus. In the numerator, you have this expression. You have you can combine, no, separate where is the real and where is the imaginary part. Like this is the real part, doesn't have this imaginary number, and this is the imaginary part. And this is a real part still. So it's like you have the ratio of the slow time signal, instant I minus 1, and you can write it as this. It's just a different form, different way to write that. And what would be the angle? The angle of this ratio will be the same as previously, right? The arctangent of the imaginary part divided by the real part. So we divide this imaginary term, x minus 1, y, I, minus xi, y, I minus 1, divided by this real part. That's another way to write the phi I minus 1 with tangent inverse, and we say that this expression, and here is the variable that we want to calculate. We want to calculate this v, velocity of particle. So it's slightly different, right? It's like in this expression you have directly, use of x and y multiplying divided by this. But in this other expression, you have these operations and arctangent of them. Okay. Which one is better? Which one is better here? Or which one would be more stable? And it turns out that this version is more stable than the other. Okay? Because if you remember, right? You remember the arctangent function. The tangent go from what? Tangent go from which rings? Can be infinite, right? Infinite can be any number. But the tangent inverse only will be between 0 and pi over 2. Okay? It's like a small range of values. Basically it's saying, okay, all these values will, the arctangent will be only between 0 and pi over 2. So even if it has some noise in this, these multiplications and division, you have some noise, the arctangent in a sense will contain that noise, limited in some known boundaries. No, but if we look at the other expression, we have x, y here, and x and y have any value. Multiplying there and subtracting can have very noisy values. So that would be another way of thinking about the arctangent to calculate the phase, and eventually calculate v, particle velocity. Again, if we do that, for example, for the pulse 2 and the pulse 1, we will obtain one estimate of v. If we do that between the pulse 3 and pulse 2, we look at the slow time signal from the samples of the pulse 3 and pulse 2, we obtain another estimate of v. We can obtain many estimates of v for the same slow time signal, for the same position. So at the end, we just average them. Calculate the mean value, for example, of the v, and that we assign that value to that position. Okay, a different formulation considers the autocorrelation of a collection ensemble of data in a slow speed time. The ensemble autocorrelation signal at delay t is given by flow velocity. The velocity of the red blood cells can be estimated using that expression. if we see here, right, we have 2 pi 2b over c f0 t b or f, no? That's phase, no? The phase difference. And that is how much? No? This is minus, no? 4 pi b 4 pi f0 dprf over c multiplied by b. All this is like a constant. Multiply the particle velocity that we want to estimate. I think in this algorithm, if you look at this term, it's just this term, right? Inverted. So the phase difference, the phase derivative in this case is calculated as an arctangent of a signal. That signal is a autocorrelation. For that autocorrelation, we have calculate the imaginary part and the real part, and basically calculate the angle associated with those dot complex numbers. And that autocorrelation here is given by this expression. It's like using all the slow time signal, right? Let me see, yeah. All the slow time signal shifted. It's like we have our slow time signal. Remember, it can have some oscillations like this, right? We can plot that slow time signal in versus tau, no? In the tau domain. Some slow time signal. And for that slow time signal, we can calculate the autocorrelation. The autocorrelation, this function in tau2, no, in tau domain, as basically the conjugates. If you consider the complex or the real and imaginary part, multiplied by the same and shifted just a value of tau of t, whether this t is tprf, the value that we know. It's basically do the autocorrelation is taking this signal, calculate the conjugates, and then shifting a little bit this signal minus tau, and just do the multiplication of those two and integrate that. And that can be done. It's not too difficult mathematically to calculate autocorrelation. And for that new signal, that signal autocorrelation, you can calculate imaginary and real part and do the ratio and calculate the arctangent. Okay, and that is not, you can calculate the autocorrelation, right? Very easy, very easy. But knowing that the imaginary part of the autocorrelation divided by real part of autocorrelation and arctangent of that is the same shifting here, maybe it's not so obvious, right? Maybe it's detailed here. If you're interested, you can read this paper, and that could be also good. How we go from this autocorrelation to the phase difference. Okay. The Kasai algorithm, the Kasai paper is a technique used. So what is the good thing of this? It's like in one operation of the autocorrelation, you are using like all the samples in the slow time in one operation. Before we need to calculate pulse second minus pulse 2 and pulse 1. And with those two calculate one estimate. Then pulse 3 and pulse 2 and calculate one estimate. And pulse 4 and pulse 3 calculate another estimate, and we say, okay, we can average all those velocities. But here it's like just all the samples in the slow time will be used in once, in one operation with this autocorrelation calculation. And the autocorrelation calculation for discretized signals, what could be here? It's like discretizing this, trying to discretize the autocorrelation would be trying to discretize this, and it's like this. This integral will become like a sum, sum, and this will become what? I think we said that st tau basically was, it has two components, the x tau and the y tau, something like this. So what would be the conjugate of this? Would be with negative here, right? X tau minus j tau, and multiply by with the signal plus tau. I think here maybe it's better to use xi for notation. I, and this would be this one, but in the next instant, right? After t. So basically it would be xi plus 1 plus y j y plus 1. And then I think there is written, yeah, okay, we have that. We can mix these two in separate real and imaginary part. So we have a sum, the real part will be a sum of xi plus 1 and this minus j plus j that are multiplying will be plus ji plus 1. And for the imaginary part will be a sum of this multiplied by this and this multiplied by this. So sum of xi j multiplied by all this minus ji x I plus 1. I think it's, and basically this is the imaginary part. This is the imaginary part, this is the real part, and we need to divide this by this. And that's here, that's what's saying here. That's the imaginary part and real part. I think only the shifting is slightly different. It's like everything incremented by 1. It's like y plus 1, y plus 1. Yeah, I, right? Just notice that it's the same, only that you reduce by 1, no? I minus 1i, I minus 1i, I minus 1i, I minus 1i, you get the same expression. Shifted one value. Yeah. And when we look only at two samples, the Kasai algorithm and the phase derivative are identical. Basically, without this sum, if you look only at two sample times, you get one estimate. But if you want to use all the samples, all the values of the slow time for all the pulses, you get this sum expression. The Kasai algorithm allows the application of wall filters and the calculation of turbulence from variance of the signal. Okay, let's see this. The wall filter, echoes from stationary tissues may overshadow echoes from moving blood. So it's like if we try to calculate with the Kasai algorithm that we mentioned, with using all the slow times at different times, at different depths. If we would this echo from tissue, ensemble Doppler before filtering. Yeah, it's like we have the slow time in this direction. Okay. The slow time signal is for this line, for example. The oscillation, low value, high value, low value, high value. Many oscillations across this. Oscillations around here, oscillations around here. Now, at the beginning, then the signals look the same. For the same depth, the signal doesn't change with time. But later, at some depth, you see the signal is changing a little bit with different pulses, different moments. So the region of interest here is around this depth. So it's like in a liver, for example, that change will occur around this area, the area where there are vessels. And this wall filter refers like, okay, how can we eliminate all the signals that come from regions that are not moving? That's the question. How can we estimate the signals from regions that are not moving? Our interest is only from regions that are moving. And if we think about the tissues that are not moving and tissues that are not changing the amplitudes in the slow time signal, how these echoes, the echoes from kind of this expression, we look in frequency. In frequency, it's like they only have values in the frequency zero. On the frequency zero, no frequency, constant. In the frequency zero, they have some amplitude. But in other frequencies, it's like no amplitude, right? Because no oscillation. So the meaning of this is that, like, if there are tissues that are not moving, how can we delete that information? It's like we need to delete the information of frequency zero. We need to delete the information of frequency zero in the slow time signal. When the reflectors move, variation in slow time domain causes the spectrum to shift towards high frequency. Imagine this kind of slow time signal, this one. Remember that we have some slow oscillations. In this case, that oscillation corresponds to 0.8 kilohertz. Or, let me see, 0.2. First 0.2. And probably this is like the symmetric part due to sampling, because this slow time is sampled, so we have many replicas, and probably we can continue with more replica. But probably this is like a sampling frequency. Okay, 0.2. And the other example that moves faster, the frequency of oscillation is bigger. So the frequency in this case is around 0.4 kilohertz. It's like a double of previous. And there is this chance also from the replica that occur will mix with the original one. There is like a limit. a maximum value of speed that can be detected with some sampling frequency. If this is a sampling frequency, let's call it sampling frequency of the slow time. Remember how much is this? It's just the inverse of the TPRF. The sampling period in the slow time, it was the PRF, the frequency, the maximum, or sampling frequency in that case would be the inverse. Okay, so this frequency, this value here, is associated with the velocity of that particle. And I was mentioning before, the static tissues, the tissues that are not moving, that signal needs to be cancelled. And to cancel the signal with frequency 0, or with 0 frequency, a filter is applied. In this case, high pass filter. A filter that keep only frequencies with some cutoff frequency. But basically this high pass tries to eliminate all the low frequencies, and especially the 0 frequency. Okay, so in other words, what he's saying in this wall filter is that the slow time signal, before trying to calculate the velocity and try to calculate the arc tangent and all those stuff, is that you need to apply a high pass filter first. Okay? And you have taken, right, digital signal processing course, and you can calculate a high pass filter with a FIR, for example, the filter. And in the FIR filter, you can, what do you need? You need, at least you need a cutoff frequency. What is the frequency that you want to use as limit? And that frequency in practice is in the range, between 25 to 100 hertz. Okay, so that high pass filter is something that you can design. You can review your FIR filters from previous courses and see how to calculate that, because that is needed for pre-processing the slow time signal. Echo from stationary tissues may overshadow echoes from moving blood. That's what we said before. And yeah, so after applying the wall filter or the high pass filter, the signal that looks constant will be deleted, cancelled, or eliminated, filtered, and you get these slow time signals now with a different depth. This is depth. This is slow time, different pulses, and it will look like this. And these are the signals that you can process. You can use like X and Y, and you will have this for real and for imaginary, and you can use those in your expression of the arc tangent. In this case, we have an example. The vessels are in these color regions. There are vessels around here, and in this case, say the high in the left, high cutoff frequency, and on the right, low cutoff frequency or cutoff setting for the Doppler wall filter. Lowest velocities are filtered in the figure on the left. The range of measurable velocities is changed in the color bar. Notice the black fringe at the center with different widths in each face. So basically here, it's like you have minus 20 centimeters per second, and red is 23 centimeters per second. showing change in direction. And they say, no, the values that look like more blue, that are observable here, no, in different positions, represent very slow velocity. No? Could be some vessels with slow velocity, but the cutoff frequency of the wall filter here was smaller than here. Here was a stronger cutoff frequency, so unless you have a longer velocity, the particles having longer velocity, it won't show. So the particles with a slow velocity, like for example here, right? There was some movement, no? Slow velocity. The cutoff frequency here was low, so we can detect that. But here, the cutoff frequency was more, so we need more velocity shown, the Doppler. In this case, it's not up here. So, like here, only the strong area, no, will show us movement, no, of vessels. These blue, no, red, blue values correspond actually to this V, to this particle velocity that we are wanting to calculate. Okay. I think only a few slides left, so, but we're going to stop here and just finish this next week. Any question? Hans, you have questions, I think, right? Email. Había algunas preguntas que me habías hecho.